Hello everyone, this is Mr. Underkoffler again. This time I'm doing a lesson on scientific notation, and eventually we'll be talking also about something called standard form. So what is scientific notation? Let's take a look at these guided notes together. Scientific notation is defined as a number between 1 and 10 taken times 10 to a power. The purpose of scientific notation is that it's a shorter way of expressing very big or very small numbers without needing to write all of the zeros. Let's take a look at an example, and then we're going to take a look at a counterexample, which means an example of something that's not in scientific notation. So let's start with the first one here on the left, 3.08 times 10 to the negative fifth. That is an example of a number in scientific notation. Now why? Because it meets the definition. The first part of a definition the definition for scientific notation is that it has to be a number between 1 and 10. If you take a look here, 3.08 is indeed between 1 and 10. The second part of the definition is that it has to be taken times 10 to a power. Clearly, we have here times 10 to the negative fifth power. And so that's why this is an example of a number that's been written in scientific notation. But let's take a look at this counterexample. Why is this 711.5 times 10 to the fourth? Why is that not considered scientific notation? It's because the very first part of it, 711.5, is not a number between 1 and 10. And so that's why this does not meet the definition of scientific notation. Even though it was taken times 10 to the fourth power, which does meet the second part of the definition for scientific notation, the first part of the definition of scientific notation is not being held true here. This first number, 711.5, is not between 1 and 10. All right, what we're going to be doing is looking at how can we write numbers in scientific notation. There are 3 steps I'm going to present to you here. Let's take a look at each of these. The first step is to put the decimal point. We're going to replace it, and we're going to put it after the digit that's in the highest non-zero place value. This will make the number between 1 and 10, which is our goal for the first part of scientific notation. Second part, we're going to figure out what power of 10 we need that power of 10 to be. And the way we're going to do that is we're going to ask ourselves how many digits must be accounted for from where the decimal point used to be to where it's now being placed in step 1. Then the third step, we need to figure out if this exponent of 10 is going to be positive or negative. If the original number is greater than or equal to 10, then it's going to be written as a number times 10 to a positive exponent. But if the original number is a very small decimal between 0 and 1, then it's going to be written as a number times 10 to a negative exponent. This should be a very easy thing for you to remember. Think, big numbers logically should get positive exponents for the power of 10 when you write it in scientific notation. But really small numbers that are between 0 and 1, like 0.0000325, those really small numbers between 0 and 1, it makes logical sense that they would be a number times 10 to a negative exponent when you write it in scientific notation. Let's take a look at the 4 examples at the bottom of your page of guided notes that are already done for you, but I'm going to talk you through them. Now, pay attention to the directions. It says express each number in scientific notation. Remember what scientific notation is supposed to be. A number between 1 and 10 taken times 10 to a power. So the first step is we got to figure out where do we need to put the decimal point so that it's a number between 1 and 10. Well, right now the decimal point on this 54,100,000 number would be at the very end of the last zero, which if I can write it here for you real quick, that is currently, here on the right end. But we need it to be moved so that it becomes a number between 1 and 10. So it needs to be put between the 5 and the 4. Now, we need to ask ourselves how many digits do we have to account for from where the decimal point used to be there on the far right end to where the decimal point is now going to be placed between that 5 and that 4. And if you count with me, we have to count the 4 and the 1, that's 2 digits, and the 5 zeros, so that's a total of 7 digits between where the decimal point used to be on the far right to where it's now going between the 5 and the 4. 7 digits we have to account for. So what's this going to look like? 5.41. Now, do I have to put the 5 zeros? No, because 5.41 is the same as 5.41000000. This is why scientific notation is helpful. With really big numbers and really small numbers, you don't need to write all the zeros. All right, let me finish this off. So 5.41 times 10 to the, now should it be the 7th power? Should it be the negative 7th power? Since the original number is a big number, definitely bigger than 10, then it's going to be a positive 7 for the exponent on the 10. All right, let's take a look at the next problem. Problem number 2. We have 2,901.5. We need to write it in scientific notation. Where do we need to put the decimal point so that this ends up being a number between 1 and 10? Well, it needs to be between the 2 and the 9, because that would make it 2.9015, which is between 1 and 10. How many digits do we have to account for? Well, the decimal point used to be between the 1 and the 5. Now it's between the 2 and the 9. That's 3 digits that we have to account for. So this is going to become 2.9015. Now, you are not allowed to make the 0 disappear when it's between two digits that are not zeros. So you cannot make the 0 here disappear like we did on problem number 1 zeros. And this is going to be taken times 10 to the, is it positive 3 or negative 3? Well, again, since the original number, the 2,901.5, since that original number was definitely bigger than 10, then this is going to be a positive exponent. Let's take a look at number 3. We have lots of zeros, and then 416. Where does the decimal point need to be placed? It needs to be placed between the 4 and the 1 to make it a number between 1 and 10. How many digits do we have to account for? Well, if you count with me, there are 8 zeros, but also the 4 between where the decimal point used to be and where it's now going to go. That's 9 digits that you have to account for. So this is going to become 4.16. You don't need all the zeros to the left of the 4. It's just 4.16 times 10 to the, now should it be the 9th or the negative 9th? Since the original number was a number between 0 and 1, like I was telling you here on the 3rd step, if it's between 0 and 1, then it's going to get a negative exponent. So this will be the negative 9th power. And likewise, a similar thing is going to happen on number 4. We have 0.0007, also known as 7/10,000ths. The decimal point needs to be placed to the right of the 7 so that we have a number between 1 and 10. So how many digits do we have to account for? 4 digits. But since this original number was smaller than 1, between 0 and 1, then this is going to become 7 times 10 to the negative 4th power instead of the positive 4th power. And there you go. There's 4 examples that I've talked you through on scientific notation that were already typed up on your guided notes. Let's have you now try numbers 5 through 9 on your own. So hit pause now on the video and do these 5 problems on your own, then hit play when you're ready for me to go over them. All right, I hope you have done that. I hope you have done these 5 problems. I am now going to show you the results. Problem number 5. Where does the decimal point need to go so that we have a number between 1 and 10? It would need to go after the 1, between the 1 and the 3. That makes it 1.35 times, how many digits do we have to account for? Well, the decimal point used to be to the right of the last 0, but now it's between the 1 and the 3. That's 4 digits we have to account for, the 3, the 5, and the 2 zeros. So this is going to be taken times 10 to the 4th. Why not negative 4th? Because the original number was a big number, 13,500. That is definitely bigger than 10. That's why it's a positive 4 for the exponent. Let's take a look at number 6. We have points 0.000000889, and we need to write that in scientific notation. First thing you got to figure out, where's the decimal point going to go? It's got to go between the two 8s, because that would make it 8.89, which is a number between 1 and 10. How many digits do we have to account for? Well, we have to account for the 5 zeros that are to the right of the decimal point, but also the digit of this first 8. And so that means 6 digits we have to account for. So it's 8.89 times 10 to the negative 6 power. Why negative 6? Why not positive 6? Because this original number was a very small number between 0 and 1. Those kind of numbers are always going to get negative exponents. All right, let me talk you through number 7 and 8 and 9 a little bit quicker than I just did for 5 and 6. Number 7 has to start as 9.876543. You do not need to put the 3 zeros, but you do have to count them when you count how many digits you have to account for your power of 10. And that's going to be times 10 to the 9th power, because you have the 876543, which are 6 digits, but also the 3 zeros, which makes a total of 9 digits. And this was a big number, so it's a positive 9. Number 8, the decimal point must go between the 6 and the 2. So we have 6.2 times 10 to the negative, because this is a small number between 0 and 1. How many digits do we have to account for? The 2 zeros that were after the decimal point, but also the 6. So that's 10 to the negative 3rd power. And lastly, problem number 9. The decimal point needs to go to the right of the 8. But 8.0 is the same as 8, so you don't really have to write it as 8.0. Write it as just 8 times 10 to the, well, how many digits do we have to account for? It's just going to be the 3 zeros to the right of the 8, because the decimal point goes after the 8, so we have to count the 3 zeros that were between where the decimal point used to be on the far right, and now where it's going after the 8. So that's 3 digits, so it's 8 times 10 to the 3rd. Not negative 3rd. The original number was definitely bigger than 10. 8,000 is a big number, so this is going to be 10 to the positive 3rd power. All right. Sorry, not next problems, but before we talk about the next problems, let's move on to the next part of our guided notes, where we're going to kind of do the opposite of what we were just doing. Instead of taking numbers in normal form and writing them in scientific notation, I'm now going to have you take numbers in scientific notation and put them back into what we officially call standard form. Now, what is standard form? Follow with me here on the guided notes. Standard form is just simply writing a number without using any exponents in times the power of 10. So basically, it's the normal form that you normally are used to seeing numbers so far in your lifetime. And there's a very simple rule. When you actually take a number multiplied times a positive exponent on that power of 10, then the decimal point is simply just going to move to the right. And if you multiply times 10 to a negative exponent, that's just going to simply move the decimal point to the left. Most people in the world are aware of this if they are familiar with the metric system, which is what most of the world uses. The United States don't use it that often, but that's why the metric system is very simple for the rest of the world to use, because multiplying by powers of 10 simply just really moves the decimal point. And so let's take a look at these first two examples here, numbers 10 and 11. We have 3.14 times 10 to the positive 5th power. Now, let me actually highlight that in yellow to be consistent with what I was doing on the guided notes right above this. Since that is a positive exponent, the decimal point is going to move that number of spaces to the right. Now, the first two spaces will go past the 1 and the 4, but then there's 3 more spaces. So you'll simply put zeros in each of those 3 spaces. And that creates 314,000 as the number in the normal standard form that we're used to seeing numbers written in. Problem number 11. This time we have 3.14 times 10 to the negative 5th power. Like we saw above, when you multiply times 10 to a negative exponent, it will move the decimal point that number of spaces to the left. So the decimal point is going to go 5 spaces to the left. Now, the first of those 5 spaces is moving past the 3, but there's 4 more spaces to the left of that. So that's going to be 4 zeros between where the new decimal point is going to go and where the 3 is located. So that, like you'll see it right here, 4 zeros, then 314, 0.0000314. And that is this number written in standard form. Let's go ahead and have you try numbers 12 through 13, or sorry, not 12 through 13, 12 through 17 on your own. You know what? If you want me to do 12 and 13 with you right now, I'll go ahead and do them with you right now. Problem number 12, we're multiplying times 10 to a positive third power. So it's going to move the decimal point 3 places to the right, which now would put the decimal point, instead of being after the 6, it's going to put the decimal point 3 spaces to the right, which would make it after the 4, and that's why it's 6,294. Problem number 13, 4.7 times 10 to the negative 4th. So we're going to move this 1, 2, 3, 4 spaces, forgive my drawing here, to the left. The first place goes past the 4, so there's 3 other spaces, which means we need 3 zeros to the right of that decimal point, then the 47. So it's 0.00047. All right, now, if you definitely have not done 14 through 17 on your own, hit pause on the video, do those problems on your own, then I will show you what the answers would have been. All right, I hope you have done that. I hope you've done 14 through 17 on your own. Let's see how you did. Number 14, 9 times 10 to the 6. You should have moved the decimal point 6 places to the right, which on this one adds 6 zeros. So it's 9 million as your final answer. Problem number 15, 1.234 times 10 to the 5th. You need to move the decimal point 5 spaces to the right, but the first of those 5 spaces will go past the digits of 2, 3, and 4. So there's only 2 more spaces to move it, which is why you only add 2 extra zeros on the end, because the first 3 spaces were past the digits of 2, 3, and 4. 2 more spaces to go, that's why there's 2 zeros. Problem number 16. 8.01 times 10 to the negative 12th. You need to move the decimal point 12 places to the left. The first space of the 12 spaces will go past the digit of the 8, which means there is 11 more spaces you have to move to the left, which makes 11 zeros. You need to count your zeros right now. Do you have 11 zeros between the decimal point and the digit of 8? 11 zeros between there, and then the 801. That is what this becomes in standard form. Now, problem number 17. We have 37 times 10 to the negative 8. The decimal point used to be to the right of the 7. You have to move it 8 places to the left. The first 2 places will go past the 3 and the 7. You have 6 more places than you have to move it. And that's why you must have 6 zeros between where the decimal point is and the digits of 3, 7. So please count that you have 6 zeros between where the decimal point is and the digits of 3, 7. All right, we now have 6 more practice problems. And instead of making these boring generic problems, I have actually given you 6 actual real-life scenario problems. This is information that I either took from your textbook or that I looked up online. So that way you had real-life examples with really big numbers with lots of zeros, or really small numbers between 0 and 1 with lots of zeros again. So you can see where we would actually use scientific notation to write these numbers with lots of zeros in real life. So hit pause, do these 6 word problems on your own. When you are ready, hit play, and I will go over each of the answers. All right, I hope you have done that. You've done these 6 problems on your own. I am now going to go over the answers. Here we go. Problem number 1. Every minute, 840 billion drops of water flow over Niagara Falls. We're going to write this number in scientific notation. The decimal point must go between the 8 and the 4 because that makes it a number between 1 and 10, like we had learned from the first page of our guided notes for scientific notation. You need to now have it times 10 to a power. What should that power be? Well, the decimal point used to be on the far right because that was a whole number. That's where decimal points are on whole numbers. But we are now moving it between the 8 and the 4. How many digits do we have to account for that were in between? 11 digits. And since this is a huge number, 840 billion, this needs to be a positive 11 for that exponent. All right, problem number 2. The circumference of the Earth at the equator is about 24,900 miles. We are going to write this number in scientific notation. Once again, you need to have the decimal point between the 2 and the 4, so that way you have a number that is between 1 and 10. So 2.49 times 10 to what power? Well, the decimal point used to be to the right of the very last digit, because again, this was a whole number, just like number 1, so the decimal point's on the far right. How many digits do we have in between where the decimal point used to be and where it now is going? There are 4 digits, and it's a big number, the original number, 24,900, so that's why it is a positive 4 for the exponent. Problem number 3, the speed of light is approximately 6.71 times 10 to the 8th miles per hour. We're going to write this number in standard form. When you multiply times 10 to a positive exponent, just like we learned above, it's going to make the decimal point move to the right. That number of spaces. Now the first 2 spaces of the 8 will go past the 7 and the 1, which means there's 6 more spaces you need after it, which is why you will notice here this number has 6 zeros to the right of the 7 and the 1, which makes it 671,000, sorry, not thousand, million miles per hour. Problem number 4, bacterial cells are very small, anywhere from 0.000079 inches to 0.00039 inches in size. Forgive me for not pronouncing those decimals with the correct pronunciations, but you get my idea here. We're going to write each of these numbers in scientific notation. The first one, decimal point needs to go between the 7 and the 9. The second one, likewise, it needs to go between the 3 and the 9, so that way we have a number between 1 and 10. How many digits do we have to account for on the first number? Well, there were 5 zeros to the right of the decimal point where it used to be, but also the digit of 7 that we have to account for. So that is 7.9 times 10 to the negative 6 power. Why negative? Because the number was small. The original number was small, between 0 and 1. Likewise, the other number, there were 3 zeros to the right of the decimal point, but then also the digit of 3 that we have to count for. So that's 4 digits total. So 3.9 times 10 to the negative 4th power. Number 5, in physics, the Planck length is a unit of length approximately equal to 1.62 times 10 to the negative 35th power meters. If you wrote this number in standard form, how many zeros would be after the decimal point? After means to the right of the decimal point, before the digits 1, 6, and 2 would show up. Now, guys, don't actually draw little waves like I was doing above here in your guided notes on problems 10 and 11. Don't do that. You're going to drive yourself insane. What you need to do on number 5 is just think. You're going to move the decimal point to the left because it's a negative exponent that you're multiplying by the power of 10. The first place to the left would be past the 1. That's the first of 35 places, which means there's 34 more places you would go to the left, which means you would have 34 zeros after the decimal point before the digits of 162. So that's how you figure out number 5 without driving yourself insane with all these little wave marks like I was doing above in your guided notes. All right, problem number 6. This one's my favorite because it's actually on a topic that I find fascinating. The SR-71 Blackbird is an actual airplane. You can look it up, history people, that can travel at a speed of Mach 3. Now, what does that mean? Which means 3 times the speed of sound. The speed of sound is approximately 7.6 times 10 to the second power miles per hour. You'll notice that's not as fast as the speed of light, problem number 3, those of you who are paying attention. How fast can the SR-71 fly in miles per hour? We're going to write our answer in scientific notation. So this obviously has more than one part to it. We first need to figure out or somehow incorporate how the problem said 3 times the speed of sound. And then it told me what that speed of sound was actually, what it actually is, 7.6 times 10 to the second power. So we need to take 3 times 7.6 times 10 to the second power. Now there's a variety of ways of doing this. One way you could do it is take 3 times 7.6, which is 22.8. If you don't believe me, you can do the work off to the side. It's 22.8. Then from here, you can kind of ignore the 10 to the second power and just focus on this 22.8 and ask yourself, forgive me, I'm switching pens here. Ask yourself, how would I write that number in scientific notation? The decimal point would need to go here between the two 2's. And so that's only one place you have to account for which is where I'm getting this 10 to the first power from. But don't forget, we also had this 10 to the second power. So I kind of just bring it over here to the right in my work. And now, from here, going a little next level on you, you can use something you learned in a previous lesson. 10 to the first times 10 to the second. They are like bases. We learned you can add their exponents. So 10 to the first times 10 to the second, 1 plus 2 makes it 10 to the third power. And now we have the final answer in scientific notation. Now, if you don't want to do that, another way that you could have done this problem is you could have taken 22.8 times 10 to the second power and made that become, well, let's see, the decimal point would move 2 places to the right, which makes it 2,280. And then you could take that number, write it in scientific notation, using the same methods that you used earlier, realizing the decimal point used to be here. Now it's going to go here, 3 digits to account for, and that is another way of figuring out 10 to the third power for your final answer. So you do it whichever way you like. There's 2 different ways of doing number 6. All right, let's go to the very last page of our guided notes, where we're going to finish off these guided notes by comparing and ordering numbers that are in scientific notation. How do we do that? Well, follow along. 3 things you got to do. First, compare the exponents. Why? Because with positive numbers, I'm continuing reading here, any number with a greater exponent is going to be the greater number from the group. All right, that's why you got to look at exponents first. Then, if you have numbers that have exponents that are the same, then you need to compare the factors of those numbers. Now, what do I mean by factors? I mean the part that is actually being multiplied by the power of 10. Let's take a look at the example number 1 that I believe is already typed up for you here on your guided notes. Now, I took this problem from your textbook. As you can see, I mentioned for you here from page 155 of the pre-algebra textbook. It says the table shows different geologic time periods. Order the time periods from oldest, which means biggest, to youngest. Now, take a look at the table here. You should notice right away that tertiary has only a power of 7. All the others have powers of 8. And that means tertiary is going to be the smallest and therefore the youngest geologic time period here from this list of 4. Because it was only multiplied times 10 to the 7th, whereas the others are multiplied times 10 to the 8th. Well, then let's take a look at the other 3, which was Jurassic, Silurian, and Triassic. We need to compare their factors, meaning the numbers that started these values here that were taken times 10 to a power. And you should notice that the biggest of those 3 factors was the 4.38, which was Silurian, then 27.45, which is Triassic's, and then finally 2.08. Again, I'm ignoring tertiaries. Tertiaries was times 10 to a 7th power. I already know that's the youngest from the group. I'm right now just looking at the ones that were times 10 to the 8th power. And so now I can put these in order from oldest to youngest. The oldest were the first 3 that were all times 10 to the 8th. And by comparing their factors, Silurian's the biggest because it's 4.38, then Triassic, which was 2.45 times 10 to the 8th, then Jurassic, and then finally the youngest, which was tertiary because it was only taken times 10 to the 7th power. All right, if you feel like you understood example number 1, you can hit pause now and do 2, 3, and 4 on your own. If you instead would like for me to do number 2 with you, then follow along. Here I go. It says the table shows the distance each planet is from the sun. We are going to order the planets of Mars, Jupiter, Mercury, and Saturn from least to greatest order from the sun. So let's take a look here at the chart. We have Mars. We have Jupiter. What's the other one they want us to use? Mercury. Oh, and also Saturn. Those are the 4 that we're looking at. From those 4, we need to go least to greatest order. Well, the least is going to be the one that has the lowest power of 10, which was Mercury, only taken times 10 to the 7th. So that is the smallest. Who's the next smallest power of 10? That would be a tie, both Mercury, sorry, not Mercury, Mars and Jupiter are both taken times 10 to the 8th. Which one has the smaller factor? That would be Mars, only 2.28, whereas Jupiter's is 7.78. So Mars is next, then Jupiter. And finally, we go to the planet that we're looking at here with the biggest power of 10, which was Saturn, times 10 to the 9th. And so that's why Saturn is going to be the greatest. So least to greatest order. By the way, this is the opposite order of number one. Number one was greatest to least. This is least to greatest. So always read the directions so you know what order to put your numbers in. All right. Number 3 and 4, you definitely need to do these problems on your own. So hit pause, then hit play whenever you're ready for me to go over the answers. All right, I hope you've done 3 and 4 on your own. Here I go, going over the answers. Problem number 3, we need to put the following numbers in least to greatest order. The first one is the one that had the smallest exponent on the power of 10, so that's 4.59 times 10 to the second. Next, we are going to go with the next smallest power of 10, which was 10 to the third, so it's 8.11 times 10 to the third. Two of these numbers were times 10 to the fourth. Which one has the smaller factor? 2.67 is smaller than 2.8 because 2.8 is the same as 2.80. 2.67 is smaller than 2.80. And so that's why next is 2.67 times 10 to the fourth, then 2.8 times 10 to the fourth, and finally we finish off with the one that was times 10 to the fifth power, which is 1.03 times 10 to the fifth power. Lastly, problem number 4, approximately 1.372 times 10 to the seventh square kilometers of Antarctica and about 1.834 times 10 to the sixth power square kilometers of Greenland are covered by an ice cap. Again, these are actual numbers here, ladies and gentlemen. Which landmass has a greater area covered by ice? All right, who's the greater one? It's the one with the bigger power of 10, which was Antarctica, because that was times 10 to the seventh power, whereas Greenland was only times 10 to the sixth power. And there you go. Those are all the problems on the Scientific Notation Guided Notes. We'll see you next time.